Hi there, thanks for watching the introduction of Async. Async is a Python package which allows you to define tasks which may have dependencies between each other and schedule them among multiple threads, or to compute them in the main thread if you don't want to have any threading, actually, if you disable that. So how does Async do that? There are two levels of abstractions that are used here. The first that I'm going to present now is the task dependency graph. So let's say we have two tasks for now, just to keep it very simple. It's task A and task B, and this is us. We are going to at some point want to get the output of these tasks. So the task graph in this case shows two independent tasks. They do not relate to each other. They do not require any input of each other. And this is a very simple case. So if you wanted to get the output of B, we would just query it. So how do we actually query output? How do we communicate to the tasks? Or how do tasks communicate to each other? So let's just imagine we want A to send items to B. Okay, here we have a new word, it's item. So tasks consume items and they produce items. An item is like a character, it's like a byte. It's the smallest thing that they can see and that they can process. And these bytes or these items actually produce or are handled as streams, which are sent through channels. So this connection here is a channel. And channels contain data. They are like buffers, like a pipe in a way. And you can have one or more writers that put items or characters into these channels, and one or more readers or consumers which take out these items to do something with them. So that's our basic terms here. We've got tasks, we've got channels, and we've got items that we send through them. If we want to consume, we are just a consumer in a way, items that are generated by B, we would actually need a channel to it, and this is how it works. So whenever we set up a task dependency, we will end up having at least one channel through which we can read the items produced. The great thing about this setup is that if there are no items, no one will do anything. And if no one queries any item, no one will do anything either. So the task will be, so basically no work will be done if there's no demand for it. Working is only if there is demand for it, which is very efficient. You can set up your network here and then at some point start consuming the items that are generated by your setup. Currently, let's just imagine A can produce two items, not more, but we are querying all items. This is done by the very familiar file object interface. So we would say read without any argument, basically like this. Excuse my bad writing. So this would mean we would read anything out of the channel. That's the same thing as if you wanted to read everything out of a file that you have just opened. And then we would actually ask B, and B would have an input channel where he tries to read everything as well. So this would give A the opportunity to actually send its two items out to the channel. While A is generating these two items, B will actually block. B will just wait, as well as we will block until as we have to wait for B. Once A has produced one item, it will send this item through the channel, which makes B unblock. So B can start evaluating that item right away, produce its output, send it through the channel so we can unblock and receive that item and do something with it in turn. Whereas these two guys, let's just imagine these are on are done in two individual threads, can continue working and send items. Once A is depleted, he will just close the channel. So B will actually unblock and realize, hey, there's no item in the channel. So I write I'm done, and I stop writing to my channel as well. I close my channel, which will allow us to unblock as well, receiving the items that have produced in the meanwhile. So we realize, hey, there's nothing more coming out of there, and the tasks are done. We have a pool. The pool is holding the task graph, and it manages a set of workers. These workers here, in our case, are individual threads, which just wait for work. This work is being transmitted through a queue, a master queue, which connects to all of these workers. So let's just imagine we have two tasks. So first, we've added task A. Task A, using the addTask function, will have yielded us with a channel which allows us to read items from A. So this channel has been given to us. Now we will add another task, which is B, but we will add B with the input channel that has been previously returned when we added A. So this automatically creates a connection from A to B and the dependency that the pool knows about. And on the other side, of course, this is still us. And when adding B, we've received a channel which allows us to read these items. So that's actually the relation between the individual entities here. Once we read items, and let's just assume we read all items from B, the pool will start working, not before. So let's just read these items, and what happens is that the pool evaluates the dependency. So it realizes, to get unlimited items out of B, I need to get unlimited items out of A as well. So it will pick A first, but the order doesn't matter in fact, and we'll send it through the queue here. And whoever unblocks first will get A to be calculated. Okay, and it does the same thing for B. Yet again, the order doesn't at all matter for this. And now I lost my selection and can try again. And B is put on the queue as well. So we shouldn't forget about the connection that is still existing between A and B. So B will unblock once A produced an item, and of course we are still connected to B as well, and we will unblock once B has an item. So now that these tasks have been assigned to the individual workers, work will be done. So A starts producing an item, and once it has been sent through the queue here, to the channel, B will be able to start working as well, and this is when they start to work concurrently. This of course means that no data may be shared, so these items are all the data they need to do the work. This is how this actually works. This is why it works without any locking or something or mutexes. You don't need that, you just need a channel which blocks until there is a new item available. Once all items have been produced, it realizes that it's done, will close down the channels, and the tasks will actually, well, go away. This looks like the tasks are physically being moved to the threads, which is not exactly what's happening. The pool will just analyze the task and chunk them up and send individual chunks to the workers to do the parallel processing. The great thing is that all we needed to do is to use the addTask function to define the relation between the tasks and read from a channel to get the output of these tasks. Once we drop the channel, which I just indicate by erasing this, for instance, it realizes that no one is able to read from B, and if no one is able to read from B, then no one will be able to read from A. So these are basically of no use anymore, and they will just delete themselves. And if no one else held reference to these tasks, then they will be properly deleted. So you don't really have to care about anything once you have added your task. You just read and drop your handle at some point, and that's it. And if you design your tasks or the functions that they execute properly, then you can have real multi-threading within Python. For example, if you have a C extension which drops the global interpreter lock, then you have concurrency, or if you do I/O, which is multi-threaded as well. Thanks for watching. That's Async.